Miles of pipelines and countless vessels operate daily under immense invisible pressure. With gas, a 500 psi pipe failure can be like detonating 80 pounds of TNT. That's pneumatic testing. But a much safer method exists, built on one simple principle: hydrostatic testing. Instead of explosive gas, it uses nearly incompressible water. A failure results in a leak, not a blast. Next, we'll break down how these pumps work, why the process is mandatory, and how it prevents catastrophe. What is this test meant to accomplish? It has two core objectives: verifying mechanical strength and detecting all leaks. To prove strength, systems are pressurized to 1.5 times their maximum allowable working pressure, or MAWP. This controlled overpressurization is not dangerous. It's a safety factor designed to reveal hidden weaknesses before service. This process specifically validates the integrity of the most vulnerable points: weld joints, flanges, and the base material itself. This isn't just a best practice, it's the law. Regulatory bodies like ASME, API, and the DOT mandate this testing. It's also required to requalify equipment after any repairs or extended downtime, confirming it's safe to return to service. The effectiveness of this test depends on a precise, step-by-step process. Let's look at how a test pump facilitates this. First, the system is cleaned and completely filled with water. Then, the most critical preparation step: all trapped air must be purged. The hydrostatic test pump is connected. It slowly and gradually increases pressure inside the sealed system, building force methodically. Once target pressure is reached, the system is isolated. Pressure is held for a specified time while technicians monitor for any drop. Of all these steps, one mistake can turn this safe test into a hazardous event. What do you think is the most dangerous error? After a successful hold, the final step is a controlled, safe depressurization, carefully releasing the stored energy. So where is this vital process used every day? Its applications span nearly every piece of our foundational infrastructure. Remember our question. The most dangerous mistake is failing to purge all air. Trapped air can release stored energy violently if the system fails. Think of oil and gas pipelines stretching for thousands of miles, or chemical processing vessels containing volatile substances. High-pressure boilers in power plants and facilities, and even the fire sprinkler systems in buildings, rely on this test for integrity. In these cases, early detection of a pinhole leak prevents property damage, environmental contamination, and serious injury. The stakes are immense, but a successful test isn't just pumping water. Technicians must account for hidden variables that affect accuracy, like temperature. If test water heats up, pressure rises, masking a small leak. If it cools, pressure drops, creating a false failure. Monitoring is mandatory. To find small leaks, a simple but effective technique is often used: adding fluorescent or colored dyes to make any seep highly visible. The job isn't over when pressure is released. Environmental rules often govern the disposal of test water containing dyes or contaminants. With these variables, how is the industry evolving to improve accuracy and efficiency? The answer is found in new technology. Let's connect two ideas: the 1.5x MAWP standard and requalifying equipment. After a repair, retesting to this high standard is the only way to certify it strong. This isn't only about finding existing flaws. It is a quality control method that validates both original design and any modifications. Now, consider the variables we discussed, like temperature changes and the need for precision. These challenges are what's driving the next evolution in testing. We are seeing a shift to digital integration, automated pressure monitoring that compensates for temperature in real time, and AI-based diagnostics. Hydrostatic testing is far more than a simple procedure. It's a foundational safety philosophy built on the physics of water. From preventing the explosive energy of a pneumatic failure to guaranteeing a new weld's integrity, its purpose is to ensure absolute integrity. Understanding how these test pumps work and why the process matters is vital for preventing system failures and meeting strict safety regulations. For the engineers, technicians, and safety officers on the job, mastering this process isn't just a technical skill, it's a professional responsibility.